Morning. Hello. Hello. Hi. 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 Oh, hi. Hi there, random stranger who's now my friend. Wow, cool. So I hope you all had a good time last night. Caught up with people you know, or met some people you didn't know before and now know as your best friend ever in the world ever. You're my best friend. I'll love you forever. That wasn't me. That was the other guy I was walking with. We're all ready for day two. It's pretty tough in the morning in day two. Very tough to start speaking. There's a couple of little announcements first. First one, if you did want a logo on your t-shirt, do remember to drop it off. We haven't had a huge number dropped off, and we pay for 30 no matter what. So it'll be quite cool if some more people drop them off. But I mean, no pressure. Keep your shirt. It's fine. It's yours. And then the other thing is bags. If you've got bags and you've brought them in, it would be really cool if you could not block the aisles with them. So if they won't fit under your seat, could you just pop them in the next room? So that's a little health and safety announcement. But so we'll get cracking. We'll get into it. Starting up is Taras from OpenNMS. So yeah, big welcome.
Good morning. I'm very impressed to see the room this full after the party last night. I'd heard there was rumors that some people got cut off a little bit, but it was also Burns night, and as a whiskey aficionado, I had a little bit to drink as well. Anyway, thank you for having me here. How many people, show of hands, have heard of OpenNMS? Yay, that's really good. Anybody actually use it? Hey, we got one in the back. So I'm here to talk about OpenNMS, which is a free and open source network management platform. But before I get started, I have to talk about Ulf the Kiwi. This is Ulf the Kiwi. We're an American project, basically, and we have a Kiwi as a mascot. And I wanted to explain why. We are, as an open source project, every year we have an annual developers conference, and people come from all around the world. And around 12 years ago, we had a gentleman from Dunedin, a guy named Craig, who came and he brought this little plush toy, this little stuffed kiwi, and he gave it to the Germans, because in his mind, the Germans had come the farthest distance the other way. And the Germans named him Ulf. And he literally became like a traveling gnome. There's a picture of him with the young ladies in Austria and in Germany, and he's been to Uganda, and so he kind of travels around. And all of our swag has a kiwi on it. So I did bring some keychains. They're up at the front, so if you guys would like. Anyway, I wanted to explain why we have a kiwi. Okay, OpenNMS has been around for a rather long time. It was started in 1999, and the first code was actually published on a website called SourceForge in March of 2000. SourceForge was kind of, if you're old like me, it was kind of GitHub before GitHub was around. There was a company called Oculan that started the project, and I worked for them until 2002 when they decided they were no longer going to work on OpenNMS, and I saw the potential. So I went to the CEO and said, hey, give me OpenNMS. And he looked at his watch and he said, well, if you're off my payroll by Friday, we'll give you a couple of servers, we'll give you OpenNMS, we'll sprinkle water on you, and you'll be the OpenNMS guy. That was the easy part. Anyone in here married? If you're married and you decide to quit your job and start your own company selling free software, I was informed that in the future, these things are we decisions and not me decisions. And we celebrate 25 years in April, so we managed to get through that. But just an important point there. In 2004, I managed, my one superpower is getting amazing people to work with me. And I managed to get a couple of people together, and we formed the OpenNMS group in 2004. And that's the company that's been kind of behind the project since then. So when I started with OpenNMS, people said, you need a lift pitch. I don't know if they call that here, but it's basically you get in the lift, someone looks down and sees your shirt and says, well, what's OpenNMS? And you've got roughly 30 seconds to describe OpenNMS. So I said, OpenNMS is the world's first enterprise-grade network management application platform developed under the open source model. Ding! I'm a technical guy. I hate, oh, we are the synergy-building, paradigm-shifting, market-leading, blah, 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 blah. So I feel compelled to break each one of these things I said down. I think we're world's best, but when I say world's first, again, we were started in 2002. There were a number of other projects that came after us. One of the most famous open source monitoring projects is called the Nagios. It actually started off as NetSaint, and we are roughly contemporaries. Enterprise grade. A lot of open source projects start off because someone has an itch to scratch. So they'll sit there and, oh, I want to monitor a server. So they'll write a script, and it goes out and monitors a server, and someone goes, oh, that's kind of cool. Can you monitor 10 servers? And they do it, and then that works fine. And then they go 100 servers, and it starts to get a little slow. And then they go to 1,000 servers, and it breaks, and they have to rewrite it and everything like that. So we started out on day one to monitor hundreds of thousands of devices. And at the end of this presentation, our goal is Internet of Things scale. And so that's kind of our thing. It's like, it works great if you have a couple of hundred nodes. I mean, it's very easy. But if you have thousands, usually if someone calls me up and I say, do you have 2,000 devices? If you've got 2,000 devices you're interested in, it's probably a good starting point for OpenNMS. If you leave here remembering one thing, well, outside of Ulf, but if you leave here remembering one thing, it's this slide. OpenNMS is an application platform. It's not necessarily an application. For example, my wife is, she works in a budget for a hospital, and she basically uses, she hates it when I tell this, she basically uses Microsoft Excel to manage a $2 billion budget. Now that's a gross oversimplification. They have expensive tools and databases that feed these spreadsheets, but it's still, she uses Microsoft Excel. If I bought a copy of Excel and called up Microsoft and said, where's my budget? They'd laugh at me. You know, because they're like, no, it's an application. You have to build your budget. Where OpenNMS really shines is when you customize OpenNMS to your environment. It takes effort, but OpenNMS is extremely powerful. It's all APIs. I mean, we did APIs before API was a buzzword. And so it's very easy to integrate. One thing that always frustrates me about large proprietary software is that everyone in here runs a business, and the way you service your customers is your market differentiator. You go out and buy a piece of software, and the software says, oh, we don't do it that way. You have to change the process that makes you unique to fit the software. With open source, especially tools like OpenNMS, you can fit the tool to your processes and not the other way around. Open source. Every bit of code we write is available under an open source license. In the United States, we have this thing called Open Core, where there's a little bit that's open source, but all the good stuff you've got to pay for. And as Gartner once reported back in 2008, it's just like, that's pretty much the equivalent of proprietary software. So I wanted to stress that the reason I'm here, there is a business behind OpenNMS that I'm not going to talk about, but OpenNMS, everything I talk about is available to you for no cost, and you're free to use it and modify it. If you type in open source network monitoring into Google, and I do this in incognito mode, we tend to be the first hit after the ads. It may change depending on your thing. I just wanted to point that out. We do have a pretty large community. We don't do any kind of SEO thing to make that happen. So the four main areas of OpenNMS. So OpenNMS is a very, very broad application, being an application platform. But I want to talk about four main things. Event management. That's usually what you folks are interested in. Things happen, you need to know about them, you need to get notified, you need to deal with the workflow. One thing that a lot of tools skip that we don't is provisioning. If you have 100,000 devices, even if you have 1,000 devices, it can be very, very hard to track moves, adds, and changes. We have a REST-based provisioning system that will allow you to take your inventory system, whatever that is, be it an Excel spreadsheet, be it actually something more formal, import that into OpenNMS, audit it, et cetera, and automate that whole process. Service assurance. I'm not sure of a good buzzword here. I know containers are a big buzzword in the server world. You've got virtualization. Back in 1999, it was SLAs. What's your SLA? Can you do 5 nines? I can do 5 nines. Can you do 5 nines? We joke that with the shutdown in the United States government, that the US government over the last year only has 2 nines. Only 99.4% uptime. So OpenNMS started out as a tool to guarantee service assurance. So that means synthetic transactions. We go out and verify that certain things are working on the network. And finally, performance data collection. If it's available on the wire, we can collect it, we can graph it, we can do thresholds, we can do predictions, et cetera. So there's tons of events. We have SNMP. SNMP gets a bad rap, but of course we support it. Syslog messages, TL1, whatever your event stream is, we support. You can enhance events. So if you get an event, you can look up a database. We have a number of customers who will put customer information. So when a circuit goes down, they'll enrich the event to add, hey, these are the customers that are impacted by this event. It's kind of like, does anyone here know NetCool? It used to be Micromuse, it's now IBM. They had a tool called Impact, and that was kind of what we do. Elasticsearch is a new, they call it the ELK stack, Elasticsearch, Logstash, and Kibana. Elasticsearch is a great event store. It's an open source event storage platform, and we can feed that. I'm going to talk about something at the end for lawful intercept that might be useful. We can create notifications, we can turn notifications into alarms, et cetera. So OpenNMS creates events. So when we monitor things, if a device is down, we'll generate a node down event, and we can say it's come back up, data collection failed, et cetera. Pretty straightforward. A lot of monitoring tools do this. Here's an SMP trap. So we have a topology change trap. So again, another type of event. Here's a syslog event. User authentication error. I tried to log in with the wrong password. You can also do custom events. We like to have people use OpenNMS as a single pane of glass, or as some folks say, a single glass of pain. So what we do is anytime we have things running, like our backup scripts, we have our backup scripts send events into OpenNMS. We have a Perl, we have a Python, we have a little tool that you can use and just send events into OpenNMS. So that allows you to aggregate a lot of the things that you're doing. One of the things that I think is really cool is we have an event translator. This is where we can enrich events. There's a standard SMP trap called link down. That means someone's pulled a cable out of a switch. You've basically lost the link light. The only thing the trap sends is an interface index. So you get a number, link down number 12. No, not number 12. So what we can do in OpenNMS is we can actually look up, in this case, index 517, and actually put a description or an alias so you get more information about what's going on. And you can do this for a number of things. Here's a picture of Elasticsearch. This is Kibana showing all these different events that you can use to analyze the events that you get in OpenNMS. Notifications. Events aren't very useful unless you do something about it. And so we have, it's kind of like a poor man's trouble ticketing system. We do have a proper trouble ticketing API where we can raise a ticket in Jira, we can raise it in RT, Remedy, whatever your trouble ticketing system is. If you close it in there, it'll come back, et cetera. But we do have a basic notification set up where you can send an SMS, you can send an email, et cetera. One of the things, I did some work in Singapore, and the third shift operators in Singapore aren't exactly the most dedicated. So we installed a speaker on the ceiling that played a klaxon when certain events would happen to wake them up. So cool things there. Now events are kind of like logs. So they happen. You get an event, you get an event, you get an event. We have a system called alarms where you take specific events and you turn them into alarm for workflow. Your ideal is to have 0 alarms. So it's actually nice talking to network operators because the idea of a circuit being in alarm or out of alarm is kind of is a lot more common. We can do what's called event reduction. This is an old slide because it's the best one I have, but if you look here, you've got a count. So on that first event, it's happened 9,720 times. The next one, 2,866 times. There's roughly, I think, 3,000, 6,000. There's roughly 20,000 events being represented here in 5 alarms. So this way you can get rid of a lot of the noise. If you have a device that's over temperature, it may send out an alert every 10 seconds or every minute. And this way you don't get drowned in that and miss other things. We have the ability to do automations, so you can match things like ups with downs. So I went and turned off HTTP on a server, and I get an outage. So we couldn't connect to port 80 on that server. When I bring it up, I get the up message. I can use an automation, and this is a default automation that ships with OpenNMS. It matches the ups with the downs and clears the alarm. And then we have another automation that runs a few minutes later that'll clear all of the normal and cleared alarms. So you can literally, in some of the network operations centers of our customers, they'll just have the alarm list up on a screen. And the alarm list is something that, if you have an alarm on your screen, someone should be doing something about it. If no one does anything, turn it off. You know, it's one of the harder parts, and one of the things that we try to teach people with OpenNMS is how to deal with going from no instrumentation to too much instrumentation. We have this ability to add notes to alarms. We call this a sticky note. Sticky is the Post-it note. You know what I'm talking about, the little yellow thing? So in this particular alarm, a sticky is tied to a specific instance of an alarm. And so in this case, you know, hey, I opened a ticket and acknowledged this alarm. When this alarm goes away, the sticky note goes away. It's gone. But you can also have a journal note, which is like a run book. So you can actually put instructions that say, hey, when this particular alarm happens, do this. Call this person, here's your support ticket, et cetera. So it's kind of a nifty little feature. And again, we have trouble ticketing integration. In the office, we use a thing called Request Tracker, RT. Many years ago, if you Googled RT, you saw Request Tracker. Now with Twitter, no, you don't get it anymore. But in this case, here we have a node loss service for the HTTP, and here's the same thing as a trouble ticketing. So if the notification system that we ship with OpenNMS isn't good enough for you, you can actually integrate with the trouble ticketing system. If you close it in the ticket, it'll clear the alarm in OpenNMS and vice versa. So it's a two-way integration. I mentioned provisioning. I'm going a little fast here because I can literally talk for the next 7 hours without a break. And I know I want to make sure that we stay on schedule. So feel free to track me down after if you have any questions. Provisioning. So provisioning basically creates an XML file which says where everything is. And you can do this through a GUI. So here's a list of all these requisitions that we have. You can do this through an API. You could actually create an XML file and then import that into OpenNMS. And each requisition talks about what devices I want to find, what their IP address is, what services there are, and we also have detectors that will go out and scan your network. If you do have like port scanning technology, you have to whitelist OpenNMS or else you'll end up, it looks like a port scan. You can also do automated discovery. You can actually point it at an IP address range, et cetera, and create these requisitions. If you have a smaller network, like the one we have at the office, I do a scan. But for larger networks, we tend to use requisitions. And there's kind of what a requisition looks like. If you do put address information in your system, we do have a nice little geographical map. I could do an entire presentation on how much I hate network maps. But at OpenNMS, we have basically two types of maps: geographical, based upon the location of the device, and topology, which is based upon whether it's layer 2 topology, VMware topology, Juniper topology, et cetera. Service assurance. Are things up or are they down? So we go out and do synthetic transactions. Everything to us is a service. If we ping a device, that device is providing the ICMP echo service. We also do some very complex monitors. There's an open source tool called Selenium that lets you to test web applications. You can create an XML file in Selenium, import that into OpenNMS, and we can automate the running of those tests. Now we have something, so here's just a picture of some of the services we monitor. I'm surprised no one has stolen this. This is one of my favorite parts about service assurance. We have what's called an adaptable downtime model. I'd mentioned earlier SLAs. So when I used to do consulting and I'd go out and someone say, I want to guarantee an SLA, I'm like, okay, what SLA? And they go 5 nines. It was always 5 nines. I don't know why. And I'd go, okay, over what period of time? A decade, a score of years, a century? And invariably they'd come back and say, it's a month. I want to guarantee 5 nines over a month. And I'd have the job of pointing out, that's about 27 seconds of downtime a month. Oh, hold on. Sorry, I got a buzz on here. Let's see if I can get my login. Oh, the service is down. That's 27 seconds. It's very, very hard to respond to something in 27 seconds. I tried to talk them down the ledge and say, what about 4 nines? 4 nines is about 4.5 minutes of downtime a month for a given service. So you have a chance. You have a chance of being able to get into the web server, restarting it, or have an automation kickoff that restarts it, et cetera. But by default, most monitoring tools poll at a set rate. 5 minutes is the industry default, every 5 minutes. So for most tools, the default outage, the shortest outage you can have is 5 minutes. So you've blown 4 nines. At OpenNMS, we momentarily increase polling. And this is all configurable, but by default, it's every 30 seconds. So the moment we have an outage, what we end up doing is we will do a complete poll with retries every 30 seconds. So we can detect that something has come back up in as early as 30 seconds. Now, you folks, I've been here a day. You folks are pretty smart, and I know at least one of you is in there thinking, yeah, Taurus, but if I had a perfectly timed 4-minute and 59-second outage, you wouldn't know about it. And that's true. If you need that kind of granularity, you just have to poll faster. But where this happens to be beneficial is if you're on call. Did anyone here have to be on call? I see a few hands. Every third week, I'm on call. And what I hate is when my phone goes off at 2 in the morning, and I have to apologize to my wife because she's a light sleeper, and I have to go in the other room and I have to fix the problem. What I almost hate worse than that, I have to say almost, is when 2 minutes after I get up, my phone buzzes again and says, oh, everything's fine. You know, my heart's beating, I'm like, and I can't get back to sleep. My day's ruined. So what this does is, by having this downtime model, I can put a little delay in front of a notification. Say, my default's 2 minutes. So I know I have 5 full polls before I get awakened in the morning, and that I know that I've really got a problem. So that's kind of cool. The big thing in the server world is servers used to be pets, now they're cattle. You're doing a lot of microservices, you're spreading things out, everything's redundant, and so you don't care as much about individual services. Well, we have a tool called the Business Service Monitor that allows you to create a model of a business and what it's based on. So if parts of it are outage, so in this case, my web service is actually degraded, but it's not down. But the parts that are down easily show up. You can create this manually. If you have this information somewhere, we have a REST API that allows you to automate the creation of business services. So data collection. We go out and collect things. If it's on the wire, we can collect it. It used to be SNMP. Now it's much more likely to be XML. Like there's APIs out there. They'll expose it via JSON or XML. We'll go out and collect data. Here's an SNMP data collection. So we can go out there and show you your bits in and out. We have a thing called near real-time graphing. By default, we have a set polling rate for SNMP. Again, it tends to be 5 minutes. But if you're looking at something going on, you can click a button and it'll poll, in this case, every 5 seconds. So you can actually help diagnose things where you don't have to sit and wait for 5 minutes to see if the problem has been corrected. There is an open source statistical package called R. We integrate with it so you can do trending. In this case, here's a bandwidth trend over, in this case, about, I think, several months. So you can see my bandwidth is actually trending down. We can collect anything. This is a soda machine in our office. I just got an email that I sold a can of Diet Dr. Pepper. So we actually go, and there's a little computer that sits in that soda machine. We actually poll it, and it comes back and tells me how many sodas are left in the machine. If you use VMware, this is a VMware topology. We can do discovery on VMware and do a lot of automatic collection from there. Now, one of the problems that we run into when we're trying to hit IoT scale is data collection. And we use a tool called RRD tool. The gentleman from Netflix who was here yesterday put up a graph, and it was made with RRD tool. It's a very, very common graphing library. The problem is it uses discrete files to store data, and you hit limits. You just cannot get a disk system fast enough to deal with it. So we have a tool called Newts that we wrote that runs on top of the Apache Cassandra project that can do millions and millions of inserts a second. We have customers who are collecting 20, 30 million data points every 5 minutes using Newts, and it's fully redundant, et cetera. So just letting you know that that's available. There's a tool called Grafana that allows you to do some visualization. We were the first third-party plugin, and we also created a tool called OpenNMS Helm, which is actually an application that allows you to manage your OpenNMS instances within Grafana itself. So you can see there's a little drop-down menu. I can acknowledge my alarms, et cetera, based on that. So we've got just a few minutes to talk about the goal. We want to do millions of devices, billions of metrics, IoT scale. So to do this, we've actually created our own little IoT device. It's called the Minion. We came up with this name before Despicable Me, but same kind of idea. You can put the Minion software in a little box. I use this thing from Minnow. It's called a Minnow box, and it's maybe about 10 centimeters square. And what it allows you to do is remote monitoring. We have customers that will do this. They'll just deploy a couple of Minions in each one of their location, and that forwards all the events up. We have one customer that's doing 10,000 syslog events a second from each of their Minions. And we're putting that in Elasticsearch for analysis. One of the projects that we're working on moving forward is called OpenNMS Drift. It's telemetry data. So it's net flows, J flows, S flows. Rada's going to talk. I'm interested in her talk because I'm going we're going to have to add whatever her features are into this. And it dawned on me for lawful intercept that using OpenNMS and our minions to feed this data, this flow data into an Elasticsearch database may help you with abiding by that law. Finally, here's a slide with resources. As I said, it's a big project. We've got a website, we have a wiki. We actually have documentation. I know this is shocking, especially for an open source project. And I think these slides will be put up. The one I want to point to, however, is this bottom one. If you Google OpenNMS in YouTube, you'll get our YouTube channel. And I have come out with a series of videos called OpenNMS 101. There's 12 of them. It duplicates our formal class. So you can follow along at home, install OpenNMS, and work your way through all the features I just talked about. They're boring, they're really long, they're like an hour each. But if you have nothing better to do, I strongly recommend that's a great way to get into the project because it is very, very broad. Anyway, thank you so much for your time. As I said, we've got these little keychains in the front if you want. I've got one left, so if there isn't one, you can come up and get mine. And thank you once again for your time.
Excellent. Cool. Thank you very much. Thank you. So next we've got Jose and Daniel from Facebook. So welcome to them.
Hello, everyone. I apologize. I have a sore throat, so I sound even more raspy than usual. But, you know, I'm basically half of the presentation, so the fun stuff is with Daniel, and he's fine. So first of all, I want to thank the organizers and the sponsors for giving us the opportunity to come share some of the things that we're working on. I enjoy this region of the world very much, and, you know, hopefully you guys can find this interesting. It's part of, you know, like an initiative that I've been trying to do where we're trying to make presentations that, you know, more than coming and saying, hey, we have all these systems and they are very big and they scale and et cetera, more like, you know, we have this problem, this is how we tackle it, and, you know, here's something open source that you can use to build upon, right, which is what we are trying to do here. Essentially, in this presentation, we're going to talk about a system that we built called NetNORAD. We'll talk about what that system does, and Daniel will talk about the open source version of it, and he will do a live demo that it's going to work great because, you know, everybody knows live demos are always awesome. So that's Daniel and myself. Marek is also here. So if after the presentation you guys have questions or want to, you know, chat about anything really, like, we'll be around, so please, you know, come. I always put this slide in our presentations because I think it helps people get a sense of the size of our network, and obviously makes understanding why we talk about some of the challenges that we talk about, you know, it makes more sense, right? So, you know, very quickly, as recent as September of last year, we, you know, two metrics that to kind of understand the scale. We have around almost 1.4 billion daily active users, and we have almost 2.1 monthly active users. So the network is pretty large, it's pretty global, and we run into, you know, fun and interesting problems almost every day. So what's the problem that we were trying to solve with our production system? If you look at a topology like this, which is a topology that's, you know, pretty prevalent in any sort of type of close, you know, deployment that you know in data center, your network might look at something like this, right? Like this network, essentially, we're showing like, you know, connectivity between host 1 and host 2. This would be like a typical network topology between two buildings. So you have a data center that has two buildings. The data center network might look something like this. This is actually quite simplified because essentially we're going 4, 6, 8. When in reality, close topologies, the layers tend to be much wider, right? Like, you know, you can very easily find, you know, depending on how many levels you have in your close topology, that this can be 12, 12, or this can be 12, 24, 48. So, you know, but like, that slide would be basically incomprehensible, so we simplify it like this. So the problem that we had was like, we have a pretty, comprehensive passive monitoring system, so the things that depends on information that we extract from devices, that we collect, that we do with like some synthetic probing to ensure service is there. The thing that we were blind to, or the thing that like was consuming a large chunk of our time, was essentially understanding, you have a service owner that tells you, hey, between host 1 and host 2, my performance is degraded, right? We didn't have like a good baseline for, what did the network look like yesterday, and is the latency the same? Is loss the same? Because like, in any large-scale network, you will have some percentage of loss because of quality of service, because of ASIC limitations, because of packet rates, et cetera, et cetera. The interesting thing is like, did that actually change? And it changed in a significant way that like is going to impact applications, right? And we all know that this doesn't even have to be lost. Like latency, like you introduce latency in one of the paths of this type of topology, and applications typically have a very hard time, right? So the system that we created for this is called NetNORAD. Why NetNORAD? Our system tends to have very silly names, and this is no exception. Net, as you can imagine, is for network, and NORAD is the North American Aerospace Defense Command, whatever. So the dude that created this was watching war movies, right? So it doesn't have anything to do, it doesn't make any sense. It's just a radar thing, so great. So what's this system actually doing? Like a lot of our automation, this system is essentially doing what a human would do, only much faster, a bigger scale, and all the time, right? So if you were a network engineer and you had the scenario that I showed you before, what you would do, besides checking the passive monitoring that like we are assuming, for the sake of argument, couldn't show you the problem, you would essentially start doing some active probing, which would be pinging, doing things like your favorite version of ECMP compliant traceroute, like Dublin traceroute or Paris traceroute, or in our case, FB traceRT, and try to gather information and figure out, okay, what's happening, right? So this is sort of what the system does, right? Essentially, we have pingers on most of our servers, or we have pingers on some of our servers, and we have responders on most of our machines. This is happening all the time, and I'm going to talk a little bit about the how of this, and then this information gets sent to a time series database for analysis and alarms, and essentially to get the value out of that information, right? How is the evolution of the system? The evolution of the system has been, we are firm believers of minimum viable products. So version 1, so you have an idea, you think that this can be a game changer type of thing. Before, we try to get people to do some sort of proof of concept and then put it on the network and see if we get any value out of it before we spend 6 months or a year developing this and doing the proper creation of that tool. And this wasn't any different, right? Essentially, the first version of this, we were reusing the ping binaries on the servers and just wrapping it with some janky Python. And we weren't even taking into account loss. We were only doing latency. And as soon as this was put in production, we started seeing odd things that the passive monitoring wasn't catching. And we said, okay, this is a good idea. We need to expand on this and continue to develop it. So the first, let's call it production or big boy version of this, we decided to use raw sockets mostly for performance and use fast TCP probes. And this worked well. We started seeing packet loss events and more accurate measurements of latency, and life was great. The caveat with this was that essentially our service owners relied on those TCP statistics to understand the health of their fleet, at least the network part of this. And we were essentially polluting that information because now we're adding all this, synthetic traffic that's not really reflecting of the application. And they were unhappy. So because we're piggybacking on their servers, we, kind of want to keep them happy. So we changed TCP to ICMP. And, this solved the service owner problem, but it revealed another one. We were hitting polarization issues. So as I showed before, most of our data center networks are using closed topologies, and these are very ECMP wide. So if you have polarization and you're only, getting 30% of the paths, then, you have a pretty big blind spot, right? So we changed the protocol yet again, and we use UDP. And UDP solved the problems that I mentioned before, and this is what the open source version actually is using. But then we saw yet another problem. So you can see how this is, iteration after iteration. The problem that we had is that because UDP is essentially running in user space, on certain workloads, on certain systems, depending on what was happening on the server, we would get, hey, we have this massive amount of loss. And the reality is that those hosts were simply congested, or that fleet was simply congested because they have a workload that's, like the type that, this is going to be forever 100%, or, it has large chunks of time where it's going to be very high, right? So we decided to add ECMP probes, again, as a, sort of tiebreaker, as a second source of signal to understand, okay, like, do we see this in UDP? Do we see this in ECMP? Okay, this is probably real loss versus like, okay, do we see this only in UDP? So is this real loss, or is that fleet congested or, busy, basically? And when you boil this concept down, you essentially have the function of a pinger and a responder, right? And pingers, like I said, run in a very small subset of machines because you don't really need to run them, in the entire fleet. Responders, we try to run on every server. So the responder, we try to make it as lightweight as possible. And the functions of this are very clear in the sense of like, if you're a pinger, you receive from a controller, which we replicated for the open source version, and Daniel will talk about it. You receive essentially what's your target list, right? Like when you're going to do your cycle, hey, who should I ping? And basically the responder replies to this. We use a lot of time stamping, both to understand where we're spending our time and to do the latency part of this. So we do this to understand, are we spending this in like network? Are we spending this on because the devices are busy, et cetera, et cetera. The pingers can have a very high rate, because like I said, it's a very small subset of devices that can be, pinging a large number of servers, and the responders are, very low, right? To again, allow us to run in the fleet in as many servers as possible. We also, as I imagine many of you have, we have quality of service deployed all over the network, and we are doing this exercise on every class of service that we have. So essentially, the pinger will set some DSCP marking to match each one of those queues, and the responder will simply reflect this back in the reply. So now with this information, we had to decide on what was going to be our unit of loss, right? What was going to be the smallest subset of like collective loss that we were going to care about. And we essentially decided to do this with the concept of clusters. And clusters, if you look at the slides, and maybe I have a laser. Do I have a laser? I have a laser. Yay. Like this is our concept of clusters. If you think about the host down here as servers, this is a top of the rack, and this is an aggregation layer, right? Which can be the first stage of your fabric, or if you're using one of the older designs, would be the aggregation layer, right? So this is this is what we define as the clusters, and this gives us the ability to detect issues between racks because you're essentially pinging each other. So you can say, hey, do I have loss inside of the cluster, right? And we'll show that in the demo. And it gives you more signal that I'm going to talk about with a better graph in one slide, right? This gives us dedicated pingers per cluster. We try to probe all the machines or most of the machines inside of that cluster. And like I said before, this gets sent to a time series database. And typically in our production system, it lags by a couple of minutes, which tends to be good enough, right? NetNORAD has always been sort of a last resort system. It's when passive monitoring has failed, or we have some sort of great failure. And we actually have another system that's called NFI, which we have done presentations on, that actually tries to pinpoint this to a particular circuit or a particular device. But NetNORAD is an older system, and it's basically more of a baseline, right? So let's see what are the signal that this can give me. So our network looks a little bit like this, or it's organized in this fashion. So we have regions, data centers, and clusters. So a region can be, for example, let's think about where we are based, which is in Dublin, in Ireland. So a region can be Dublin, right? So inside of Dublin, you can have two data centers, Dublin 1 and Dublin 2. And inside of those data centers, you will have clusters, right? Which is, like I said, a collection of top of racks and servers. So with NetNORAD, we can have multiple signal. Let's, for example, say signal 1 would be, hey, I'm going to do pinging within my data center, right? So that would exercise the data center network, right? Another signal would be, I'm going to ping between data centers, right? So inside the same region. And then finally, you could do, I'm going to ping outside of the region. So for example, like I said, if you think on the left that we have Dublin, then maybe on the right we have the US, or we have APAC, or we have another region. So this gives that operator that's getting that, hey, we have some sort of problem already, like some signal or where to start, right? Because if this is clean, right, it means that the data center network is probably OK. If this is clean, so in between regions, it means the backbone is probably clean. And if you only see loss here, it probably means that you have some sort of issue with your metro connectivity. Some sort of the issue between, in this hypothetical scenario, doubling 1 versus doubling 2. So it gives you a starting point, which in networks of our size tends to be important and relevant, right? And now Daniel will talk about the open source version, how it works, how you can mold this to be what you need, and we'll do the live demo that's going to go great.
Hello. So yeah, that's basically how NetNORAD works for Facebook. We are going to talk about the open source version that we have. This is basically a small proof of concept. It's not like a download and install solution that you can start running in your network. You could, but the idea of this is basically getting you to do some coding, understanding that to build something like this, you don't need to run thousands of lines of code. If you have like the main components that we have open source in the past, with just a few hundred lines of code, you can have a similar solution to what we have in our network. So the main component that I was mentioning is UDP Pinger, okay? UDP Pinger is a C++ library that allows you to do pinging, and let's say it gives you pingers and responders, okay? And this is the main component. This is like the most complex piece of code that NetNORAD has, okay? And this is open source for several years in the past, and right now what we have is like the glue to put this all together with some hacky Python, let's say. So basically, if you are a human, we are not talking right now in automation, and you are that guy down there, and you want to ping a host, okay, I'm going to ping this guy that is in X region, X data center in any cluster, okay? You go to your host, you do a ping, and from that pinging of that destination, you get information like, hey, this is the loss that we are detecting, this is the latency, and with that information, you make decisions. Like, hey, that host is bad, the backbone is running bad, and you start your troubleshooting from that point. So basically, what this OpenNMS does is automating that process. And to automate that process, we basically need a controller, okay? A controller that is built on Python and Flask. This is the most simple code that you will ever see, okay? It's a few hundred lines of code that takes care of that human process that we talk about and doing it in a more automated way and in a way that it can scale. So the controller has also a SQL database. It keeps the information from pingers and pongers, responders, in a SQL database. And one of the things that it does is the pingers and the pongers will register to the controller, okay? So you basically deploy all your pingers and pongers, they go to the controller, and in there you register classic stuff like what's the IP, and a few labels that you can define. This label could be, for example, like where is the data center, the cluster that this pinger or ponger is, et cetera, et cetera. This is customized. You can modify it to your needs if you don't have that, let's say, hierarchy of a region, data center, cluster, et cetera, okay? So every time a cron job executes on the server, it will get the pinger to, let's say, after we have the registration process done, the pinger will contact the controller and will ask, okay, give me the list of all the targets I need to ping, okay? So let's say we have 1,000 responders in a network, 1,000 pongers, okay? And that list will go to the pinger. This will trigger then the actual pinging of that devices. So we have one pinger in here, one responder on the other side. Pinging will happen. We record latency and packet loss, okay? And that information goes into InfluxDB, okay? InfluxDB is an open source time series database. It's freely for anybody to use. It's pretty simple to install. And this is like one of the main components of the solution, because you can work directly with the data that we gather with the pingers and pongers and play with directly with InfluxDB. You don't need anything else. But we like UIs. We like to work with the information that we are gathering for all this pinging in the network. And we have, let's say, the UI of this solution is Chronograph, okay? Chronograph is just a way of visualizing the information that we are storing in InfluxDB, but you could use other solutions like Grafana is also a good way to process the data that we have in the database, okay? And all this code is in our GitHub page. In there, you will find a pretty detailed guide on how to install the controller, all the libraries, how to install the pingers and pongers, everything on how to have a solution of OpenNMS running, okay? More importantly, we have created a few Debian packages that you could use to install this in Debian systems. This is basically to simplify the deployment of UDP pinger, okay? UDP pinger requires thrift and requires libfolly. These are kind of, I mean, it's not impossible, but it takes time to compile them and to have them running like in a good way. So we basically did these Debian packages to streamline the installation process, okay? And we are not going to talk about the scary part, that this is the demo. Basically, on this demo, we're going to be seeing the thing that we want to show you is basically how we detect packet loss between rack 1 and rack 3, okay? We have a pretty, this is like a better topology to show you what we actually have. We have all these running in the cloud, okay? These are basically virtual machines running on a cloud provider in actually close to this location, okay? So close to Madrid, we have a few instances running in SFO and in Melbourne, okay? So we have all these instances running, and the first thing that we want to show is basically how we detect packet loss from rack 1 to rack 3, okay? Basically what we're going to do is we're going to introduce some fake loss in the network, okay? We're going to force some packet loss in the network on rack 3, and with the solution, we will be able to see how this loss is visualized in Chronograph, okay? The other example that we want to show is how we detect packet loss from rack 1, this is one of our pingers, to rack 2, okay? Basically, how the topology is laid out is that every rack 1 is a pinger, okay? And all of them are responders, are pongers, okay? So we have a full mesh of pinging to every device in the network, and with that, we are able to detect the packet loss or the latency of the network. So let's go now to our screen, and this is basically Chronograph. It's a pretty nice way to visualize time series information. It allows you to create alerts, create alarms, post things to Facebook, or Your events can go to Facebook or any other social platform that we are not going to mention. Just go to Facebook. And so let's go to our dashboard. This is basically a setup we did for this presentation that is basically how Cluster 1 in Madrid see the network. And as you guys can see here, while I was speaking, Jose put our latency, our packet loss rule in place, and you can see how we are seeing some packet loss between Madrid, Cluster 1, Rack 1, to, I kind of lost it, to Madrid, as you can see in here. Okay, here's the location of what's the destination that is having the packet loss. So Madrid, Cluster 1, Rack 3. So within the same cluster, we are detecting some packet loss. Rack 1 is detecting packet loss to Rack 3. And Jose removed the packet loss, and now it's gone. So we are back to looking at 0 packet loss within our cluster, okay? If you go a little bit down, this is the other test that we wanted to do. While I was also working, Jose introduced that packet loss in SFO Cluster 1, Rack 2. Okay, remember that we saw that in the diagram. And in here, we are having a 0.73 packet loss. That's basically 73% of packet loss. So there is something terrible happening there. You should probably drain that cluster or burn it or replace it, whatever. Okay. So this is basically the interface. On this side, we have, like I said, the packet loss, and in here we're measuring latency. Okay. Look at the latency within the cluster. Of course, is going to be pretty low. It goes a little bit up, but not that much if the latency is measured between cluster. But it actually is. We can see that we are not lying, and this is running in this actual location because we have a pretty big latency to Melbourne. That's 277 millisecond latency to Melbourne and 92 to SFO. This is the view from Madrid to Melbourne and Madrid to SFO, okay? And yeah, this is basically the interface. Like I said, with Chronograph, you can create your alerts, post to Facebook, and do a lot of amazing stuff. But you could also go directly to InfluxDB and work with the data. You create your events, you create your alarms, and this will allow you to have something similar to what we have within Facebook. Like I said, this is not like a box that you deploy and you forget about it. This is more like a proof of concept, get you to see the code, see that it's pretty simple, the code that we have in the controller, and that just modifying, just putting a few lines here and there, you can have something like this running in your network. So let's go back to here. Let's say, so this is the two things that we tested. And yep, that's basically everything. Thank you very much for listening to us. And do you have any questions? Yeah.
Is this working? Yes. Are you planning to keep updating the code, or is it just like a proof of concept that's just going to stay as it is?
I mean, right now it's just like a proof of concept. We don't have like in the roadmap making this bigger, but it could happen in the future.
It basically depends on the community, right? So like if we get, hey, how do we do this? How do we, if we get requests, if people want to actively work on this, we'll help people, right? But from our point of view, like this was kind of like we did it in we do internal hackathons, and we did this over an internal hackathon, and it does what we kind of want. So like, we put it out there and we do this presentation. We've done it a couple of times. And like if the community comes back and say, hey, can we expand this, or can we integrate this into, OpenNMS, for example, we are more than happy to help, right? I mean, the brains of this is the C++ library that does all the heavy lifting, right? It's the thing that allows you to have, a single finger doing millions of packets without melting the CPUs, right?
So if we were to adopt it at TradeMe and contribute code back, would you put it in the same place, or should we put something that inherits it, or what?
Yeah, I mean,
Yes. If someone contributes and gets the code updated, we can publish in there. So.
Anyone else?
more questions? Yes? No? Cool. Thank you.
Thank you.
Just need to know how that works. My name is Igor, and my family name is really complicated to pronounce, especially for English-speaking people. I'm originally from Russia, and I work for Vocus Communications now in New Zealand, so AS 9790 currently. So I've been talking before, last year, about the actual using the Ansible and beyond, and today I'm going to be talking about the beyond Ansible. So I think talking about more kind of the event-driven infrastructure approach and what you can do with that, and the modern things which other people are going to be talking today, like streaming telemetry with OpenConfig and other things like that. I'll start with the overview of what are the common network automation systems which are currently used and what it tends to be more popular, and that's the thing. So let's begin, kind of. So the most popular ones are just free, really. The third one, it's not a complete tool. It's like a Python library, and two of them are actually using that one under the hood and stuff like that. So Ansible, SaltStack, and Napalm. Ansible tends to be more the biggest community around it, and it allows you to do lots of different things. Lots of people contributed to it, and it has different modules for, the vendor support has lots of that. We're gonna get back to that. And SaltStack, I think it would be a different talk if the SaltStack existed when I started doing the network automation, but where SaltStack is now and where it was when we kind of started working on that, it's two different things. So. It's if you're actually starting it now and you're trying to be into it, it's definitely a thing to look into it. A lot more people coming into SaltStack and trying to learn more about that and actually use it. I think maybe Cloudflare, using it for the network management system, but I'm going to talk about that more. So Ansible doesn't have an agent. It's like a CLI tool. You just run it. It's just the Python script actually, and it requires not much dependencies. It works on macOS. You can run it from your PC. You can run it from the server, from a jump host, or things like that. It doesn't quite work on Windows, so you can't use the Windows as a platform to manage your boxes. You're going to have Windows. But currently on Windows, you have it's called Linux on Windows, I think. So that thing allows you to run the Linux kernel inside of Windows, and I think you could use your standard Linux tool to install Ansible and run it. There's no problem with that. So you kind of can run it in Windows, even though it's not technically Windows. It's actually Linux inside. Easy to install, inventory variables, like you need data, right? So when you're configuring something, you need data, like interface names to configure, BGP neighbors to configure, the addresses, all of those things, variables. They stored, Ansible uses just plain text files, YAML format to actually store the data. So you can just have the different, they have best practices and the directory layout, which allows you to actually store it in different systems. So there will be different groups, and there will be different hosts, and you can mix and match. So you can actually have variables for the whole group. So that means it's going to be applied to they're going to be used for the whole group of hosts, or you can have per host specific things like host name, for example, and a management IP or whatever have you actually. It's written in Python. extensible by writing your own modules, right? So everything really is a module side of Ansible. It has, so the template to generate the config, templating engine it's using is called Ginger. It's a Python templating engine. So that's one module. So I'll talk about that more when I show an example of the playbook, how it runs. And AWX is actually an open source version of Ansible Tower. I'm not sure how many people actually heard of that. It's a commercial offering from Red Hat. You can use it and you can buy it. But recently they actually open sourced the AWX. I have actually tried it. You can run it in Docker, so it just uses Docker containers. It's just spin it. And what that allows you to do, the Ansible by itself, it doesn't actually have capabilities to run on schedule, to run and check something. Often what you want to do, you provision something and you want to keep this state, right? So if someone tomorrow, I don't know, provisions the peering or prefix lists or, I don't know, whatever config you want, like syslog service, just some simple examples of that. So what happens is in Ansible, you're going to have to run again, like tomorrow, or just do a cron job, which is like not really reliable sometimes, and like how you're going to track what actually, you can put it in the files, but like it's not. But the AWX allows you to actually do it automatically, and it has like control separate groups. The admins can, admins and just normal users, you can separate rights in terms of, or people can only run, they cannot actually edit the playbooks, and all of that is built into AWX. And the variable storage changes from just being plain files. They actually have a database in the web interface, so you actually interact with the AWX via just a web interface, so that's how it works. I don't have slides on that. I'm not sure how much uptake, how many people are actually using that. It was open source maybe a couple months ago, maybe like 4 months or something, so it's kind of a new thing for them. And they still run the Ansible Tower as a commercial offering. Vendor support for Ansible, and that's not it. Like, actually, there's like the list going to go on the whole slides. I just wanted to show some of it. So all the big guys, all the vendors are supported. Some of us are less supported. For example, the Cisco iOS, the classic iOS, and iOS XE. Like, it's really hard to automate that thing. It's almost impossible. Like, because the config is scattered all across the, all across. You can't really kind of put the whole thing together. So people actually wrote the separate modules to just manage VLANs, then the separate module to manage VRFs, separate modules to manage interfaces and things like that. And Classic OS, for example, doesn't provide you capabilities of like rollback, commit, and all kind of stuff. So therefore, like any change you make, if you stuff it up or if the Ansible stuffs it up, that's going to be a disaster, like total. And then because it doesn't have rollback or anything like that, it's unrecoverable. You lose access, everything just did. So I don't know, people actually use the Ansible to manage Cisco iOS devices. I personally, it sounds scary, really, like how, especially like being a service provider. So it's a different kind of thing. So for that, but it works fine for iOS XR. And Juniper, and now Alcatel, well, Nokia now. So the Nokia now supports from version 15. They support XML and NetConf. I'm going to talk about that more. So that's how the playbook looks. So that one actually provisions the, just as kind of sample. It provisions the inbound LSPs and MPLS network. So you have a couple things in here. I'm not sure if you have a laser here. Somewhere, I guess. All right, to a button, all right. Oh, okay. Yeah, so that's just the name, and that's just hosts. You can reference host groups, or you can reference just the host names, individual ones. Connection and local, meaning it's like actually not using the Ansible has a built-in SSH model, like providing a transport. So in this case, because we're connecting to network devices, actually not using the built-in connections. I think they actually rewriting that code, which is going to be a totally different thing. I think maybe they already did, but I'm using almost the latest version, and ourselves, I have written some of the modules to to provide capabilities like, just even simple stuff. I'm going to talk about that more a bit. This just provides the prompt for username and password if you want. You can do key off on some of the vendors as well. So that's what I was talking about. So that task is just generates the config, and it stores in your local home directory, right? And after it, the other task, which is that one, is going to actually pick these files up and actually provision that config onto the device. Yeah, it's just this kind of little sample thing. This one is just checks that the port 830 is actually open and netconf is active. So majority of the changes, like for Juniper iOS XR in the new Nokia TMOS 15 and above, it's actually using netconf now to configure devices. It doesn't do CLIs. It doesn't actually log in or enter commands as humans. It actually interacts with the XML. It's an XML protocol. I'm going to talk about that more. So basically, see the Ansible has the modules which come with Ansible. So you just install Ansible and it has modules. But it actually has other things as well. Like Junos, they have Juniper, they have their own modules. And I think probably Cisco do as well. So what happens is the difference is little tiny things are important, right? So that's why, for example, I'm using that. So why it's used here is just because the check commit wait thing, at least when I was testing it and I'm using it, this standard module which will actually fail on the dual routing engine devices, because what it does somehow, it just mixes it up and then starts committing while the other one is actually still in progress. Things like that. So that's why the Juniper native modules written by themselves have that check commit wait. So it actually waits for the first one to finish and synchronize the DB bits in the routing engines, and then it does that. But yeah, I'm going to be talking more about the more interesting things. So SolStack. SolStack actually needs an agent if you're managing Linux boxes. So, but in case of networking gear, it actually does the proxy minions, they call it. So the number of hosts are going to be managed by a proxy minion. That's going to be, maybe several hundreds and stuff. I think they have, not to say, big limitations, but every device is going to actually create a process which is, I don't know, like 45 meg in memory. So you only can actually, you can actually manage limited amount of hosts per the proxy minion. It's not really a big thing. You can spin up multiple of them, and the master node manages all the minions anyway. And the cool thing about it, this is more modern, right? So that one, the SaltStack has encrypted communications with all the proxy minions. They have I'm going to talk about that. So it has API, has the built-in data cache and stuff like that. So every time it runs, the data is cached and stuff like that. Plus, it can be, verify the state and bring everything to the desired state, and this is more kind of modern approach. And they currently provide the event-driven infrastructure, so they can actually pick up on logs and collect logs and events from that. So I'm going to be talking actually more about that. Napalm is just a Python library. What it's trying to do is trying to abstract all the differences in configuration away. The differences configuring small things like on Cisco, Nokia, and Juniper. So those differences are abstracted away. So there's one way to configure BGP, and you can use it. And what happens is you just tell it to configure Cisco, Juniper, or Nokia device, and it goes and configures them with the same config kind of. But Ansible has the modules which are using Napalm underneath, and the SolStack is actually using that for just normal things, right? So the vendor support, though, is not as broad. So it supports Arista, Cisco iOS, and iOS XR and XOS. But some of the support features in here, they're limited because what they're doing, they're trying to replicate the features with software. Like iOS, as I mentioned before, doesn't have the rollback or commit or candidate commit capabilities. So what happens is they mimic that behavior inside of the Napalm library. So it works. I personally don't use anything for classic iOS, so I don't really want to deal with it, but it's a different story. Yeah, so in our case, what if none of the tools actually 100% fit the requirements? The service orchestration inside of those tools, we are a service provider, and we have different challenges compared to like Facebook and stuff. If they have like millions of users and billions of and terabits of traffic, we do have gigabits, let's say maybe 1 terabit, but the difference is we have like number of VRFs, and the number of subscribers we manage is a lot, right? They will have thousands of VRFs. Every subscriber has different things: L2 VPNs, L3 VPNs, all kinds of those things. Plus some of the things like on binges we have L2TP tunneling for to provide services to the customers. All of that needs to be managed, and actually adds lots of complexity. It's not as easy for us as for like the enterprise guys maybe to manage that, because it was different vendors, all sorts of services we provide, and it's all kind of meshed together. So in Ansible or SaltStack, currently Cisco, I think, are trying to introduce the service layer API, they call it. So what they're doing is actually finally some of the vendors actually opening up and trying to provide the API to actually create a service, right? Creating a VRF on one box is not a service. Like, you wouldn't buy that service. You don't want VRF on the box. What you want a VPN created across like hundreds of boxes potentially, or 50 boxes, and all of that needs to be verified that it's up. And like if it's a manual job, like people will take, I don't know, 30 minutes to verify it. Just verify all the interfaces are configured, all the BGP sessions are configured inside of VRFs, or if you have different routing protocols, it can be different. But all of that, and it takes a long time. So that's why you probably want to have some kind of like an event bus, which actually feeds back. I'm going to actually talk about that. So combined approach, that's what I've been doing for some time. So Ansible is still used for configuration management. The configuration management is only a part of the problem, right? So configuration management is important, but you actually have other things. Like with emergent APIs and things like that, you can actually affect or actually influence the routing decisions based on different things, right? So you don't have to actually reconfigure things to per se, change the configuration per se to do something like this. There are things like currently Juniper has Jet API, so that allows you to change firewall rules on the fly. You are actually directly interacting with the box, and the time it takes to actually apply the new shapers or polices are like minimal. Like it's less than a second compared to for you just changing the configuration, waiting for that to happen, and things like that. Juniper used to, like, they have a YouTube channel, they have a demo. They did that for like changing conditions, like satellite links, and the signal to noise ratio is dropping, and after the bandwidth on the satellite channel is actually reducing, and what they do on the fly, they know how much megabits per second the link does, so they will reconfigure all the polices on the fly with that, not changing the configuration, so that kind of thing. So Ansible is still used for configuration management, and a big part of what I'm going to talk today about is the Apache Kafka that provides data streaming processing pipeline. So all the data we collect from the devices, we use different methods to actually do that. It goes into Kafka, and there are different things actually consuming that information from Kafka. Kafka is an open source tool. LinkedIn, I think, are the ones which originally wrote it, or at least have influenced the project. Now it's part of the Apache Foundation. If you know what the message queues are, so that's kind of the same thing, but it's not exactly the same. So Elasticsearch and InfluxDB are still used to store the data, but like the collectors which collect data from the devices don't actually write back to them directly. So everything goes into Kafka, and then after it outputs to different systems. And we have, I'm going to talk about that, and then it's internally written things, quite a lot of them, to actually collect the data and put it into Kafka, read off Kafka, react to events, or react to things, or to enrich the data. And Capacitor is a part of the InfluxDB project, and then themselves, it can actually get the stream out of Influx, and it can produce the different things. So this one is an open source processing tool. So it can do anomaly detection. So if you have like a graph with saying, okay, so the traffic was 30 gigabits today, can we have a look at the data for the same day the last week and see if it's still the same or not? And based on that, you can do kind of things, and you can say, okay, so why is that not the same? It should be the same. So we fire off an alarm. It can do different things as well, like I'm going to talk about the capacitor more and so. So first of all is in Ansible and how that works. So we don't actually, we have our own internal inventory, which stores all the data. So there are several things like agents running auto-discovery. So they will discover the interfaces, hardware, and all things, and they actually store their data into inventory. So after that can be used by different various systems like monitoring or telemetry collectors to know what to collect. Right, so the similar idea with the OpenNMS they were talking about in terms of actually running that. We just want to actually abstract that part away, so we can easily replace our monitoring system or any of our systems with anything, right? So most modern systems, monitoring systems, have API, so it would be easier for us to write some kind of the connector which feeds off the inventory and then provisions all the devices in there. So that's why it is actually separate. So it feeds into monitoring, feeds into telemetry collectors in Ansible as well. So when you run Ansible, there's a script, and that script runs, connects via an API connects to that storage, gets all the data, all the variables it gets from there, and after it uses the data to produce the templates and output to that one. It can be, we also have like a web interface to it, so if you want to check something or you want to change something or can introduce a new device, it's gonna, you can just update that. And various like semi-automated tasks are running that. So because it has an API, various people have written some things to actually interact with that, do something about it. It has two APIs. It's written in Go, so which is another thing I'm going to talk about. It has REST and gRPC APIs. gRPC, if you haven't heard it, is Google Remote Procedure Call framework. That's actually heavily used in networking gear nowadays. So that's the thing. If you haven't heard about that, you kind of need to read about. And it's going to be kind of replacement. Looks like it's going to be a replacement for SNMP, and a lot of vendors have implemented the gRPC. gRPC for streaming telemetry. I'm going to talk about that as well. So dynamic inventory scripts, the Ansible built in, like the Ansible has a standard way of actually doing the dynamic inventory. So it can run your script. You just configure which binary or which script to run. So every time you run Ansible, it runs that script. That script can do anything you want, however you want to produce the data. It doesn't have to be the same way as I was showing. Can do anything you want. Can you connect to your own storage? Can connect to any monitoring system if it has inventory there, pull the information, and after it outputs, your script must conform to the standard. It outputs JSON. Ansible reads the JSON in standard input, and then after it can actually use the variables inside. As I mentioned before, there's two ways of configuration management. One way is just to use template module for everything. You have a template processing kind of pipeline. You feed data into that, and you produce the config, and you do it. For iOS, I don't think it's really possible to do it. For the classic iOS, that's why they have like hundreds of different modules there, which configure specific things. So your playbook will consist of 3 or 4 or 5 different steps, which configure VLANs. Then they created VLANs and configure interfaces, sub-interfaces, BGP, and things separately. At least that way, it's more reliable and it's not going to break things. We use version control for all the Ansible playbooks, and the playbooks and templates are stored in version control, so the team can interact and work with each other and things like that. So if you don't not using version control, you should really. Apache Kafka is the interesting, most interesting thing of that. Is a distributed streaming platform, and it just basically does the pub/sub interface. So, but it's a bit different from things like RabbitMQ. For the biggest thing with that, it actually stores the data. Once it delivers the message, it actually doesn't delete it. So, which is a big thing. When you have I'm gonna go. So the stream history, so it provides the stream history. So once the message is delivered, you can configure the amount of time it stores the messages, can configure the by size. So when it reaches a certain size, the logs reach a certain size, they can actually rotate or things like that. It has a wide adoption, lots of people using that. Not necessarily in networking industry. Lots of people are using it for in the web to actually provide the pipeline to when you're clicking everywhere on the page, like lots of LinkedIn, on LinkedIn particularly, they just talk about that. It's all the events which you click in there, they go into Apache Kafka and then process, and then make when you move to a different page, they process the data, and then they make the output of that, kind of the algorithm where they show you what you want to see, and that's how it works. It works via Kafka, some of that. So that's how it looks, right? So they have different, in Kafka, the terminology is these producers are the things which are written into Kafka, the consumers are which are actually subscribing to events. So in our case with networking, what it does, the producers use different interfaces to interact with the devices. Like, we really have 3 different choices: SNMP, NetConf, and the gRPC streaming telemetry as well nowadays. So for some of the routers, we're trying to aiming for just removing the SNMP entirely. So we probably not going to use SNMP. We have enough information from NetConf and gRPC to do it. It's really possible with Juniper and Nokia, I think. For Cisco, I'm not sure, because we have much less Cisco shop nowadays. So the producers can be anything really, but like in our case, just related to networking is actually using that. The other thing I wanted to mention, we use there's a WAND project, and we use AMP. AMP is kind of like a replacement for your Cisco SLAs. If you know, like Cisco has the configurable IP SLA thing, and you configure it, but it doesn't scale well, because like we tried it before, trying to build a mesh network with small Cisco devices. The CPU goes through the roof, and it doesn't work. So yeah, guys from WAND are actually writing a replacement for that, which you can install on just a server, and it can produce other things in there, like I think latency. We managed to get several things from it. MOS score, if people know, is like a voice metric. We can get MOS score, we can get latency, we can get the packet loss and all kind of things. And and that currently doesn't feed into Kafka. It still goes into InfluxDB. It's been around for, well, I don't know, we use it because of the problem with the scaling. You can't really scale the Cisco thing, so that's why we use it just internally. That allows us to enrich the data. So imagine there are events that are coming from the devices, like your state. Well, for example, we run MPLS networks, so it will be LSP states or BGP state and everything. And plus, you have that data which is coming from AMP. And now you understand more about when things are happening. Like one of the links goes down. Now some of the LSPs, there's an FRR event. So that means the fast reroute have switched the LSPs and they're running on bypass. And vendors inherently have bugs and stuff. So sometimes it just stuck in there forever. And to actually troubleshoot some of those things, you would have to log into like 50 boxes at a time. That actually saves you time. So you don't actually, you don't actually have to, go through those things. So what tends to happen on the, in a lot of devices currently, they use protocol buffers as an encoding format. Protocol buffers is like a binary format. Think JSON, but without field names or anything like that. When it goes on wire, it's just the values and stuff, just values, and you need both sides need to actually have the data structures ready to accept that, and they actually know the format. Typically, there are protocol buffer files provided, so your code is generated. So your data structures, which you use in your favorite language, it can be generated for various languages, not only one. It can be, Python, C++, Go, PHP, other things as well. So as I mentioned before, collectors use SNMP, NetConf, and gRPC streaming telemetry. So NetConf, we're gonna just quickly touch on that. So NetConf is a standard. It's an XML-based protocol, typically used over the SSH as a transport. There are a variety of the modules. Cisco and Nokia and Juniper, they all have that implemented. Some are better than the others. Cisco, I think, particularly notorious for doing different things. So when you talk to one API, it produces one output. If you talk to the other one, it produces different thing. So not really so much standard, but it's getting there. I think the new iOS XRs are actually fine. Nokia, they just what didn't used to be the case, but it is the case now. everyone uses it to configure the device, but there's no way to actually to check if you configured, as I mentioned before, we configure like VPN on 50 devices. We want to have this structured data back saying, okay, we've configured that, and now the whole thing is up. But previously, for Juniper, it was the case, but for Alcatel, it's not. Like when you ask for like show interfaces, it actually outputs just the same output you would see on the CLI, but wrapped in XML. So like, that's not really well-structured XML thing. Yeah. So like, it's the same as parsing CLI, so it's not really good. We still do parse CLI, though, for some of the things to actually store the data as well. Unfortunately, but a lot more things are coming in. Streaming telemetry with OpenConfig and gRPC. The OpenConfig has two parts of it. One part is the streaming telemetry, the other part is the configuration. I'm not going to talk about configuration today because it's just takes way much time to actually do it. But going to talk about the streaming telemetry. That seems to be the standard what everyone converges around. All the major vendors actually support on it. So what you can do with your simple code, they have examples for Python and Go. I think Python and Go actually prevail all around the industry in terms of like what you do, like only two implementations really. Like whenever they supply you something, it tends to be examples Go or Python. I personally write Go. Other people use Python, it's fine. So gRPC is a framework, so designed by Google. So what you can have, you can subscribe to events like interface counters or CPU or memory. Even now, you can do the hardware states for everything, and it streams it to you, and you say, okay, I want that information every 10 seconds, and it just streams you constantly. So that allows you to have much more granularity, no polls anymore. So we're getting into the place where we don't have to poll anything with SNMP. And typically, because they supply you data models, you, like instead of MIB files that are complicated and cumbersome to actually have a look at, that's actually well-structured things you can understand better, and you can generate code for your favorite programming languages. You don't even have to kind of think about that much. So gRPC just provides structure, transport. Data structures are defined in Yang. You actually don't need to use it much because most of the vendors will supply you files, which you can, after it, you can generate code from those files, which they call protocol buffer files. And they describe not only the structure or format of the messages, they actually describe other things like the RPC themselves, like methods for your language. Open source collectors, they do exist. Juniper wrote their own open API collector. It uses netconf, and now it uses the gRPC protocol buffers for it. Telegraph, it's a part of the InfluxDB thing again. That can collect via SNMP and output into Kafka as well, which is a good thing. If you don't want to write your own code, you can actually use that to output into Kafka. And after it, you can use the other things to actually pick up from Kafka. FluentD has some modules for Juniper and Cisco, so it can actually, you can configure that, and it can get the stream from Juniper and Cisco and then output into different outputs as well. So how those things like FluentD and Telegraph work, it's an agent and it has input and output, so there are various inputs and various outputs, so you can actually do that. Why I think it's so important for network automation? Because you need to verify, as I mentioned before many times, that you have to verify the state of what has been configured. Ansible is good for things like you're configuring, for example, like something which you set and forget. You have in Juniper, you have a system stanza, like the part of where you define all the syslog servers, NTP servers, users, and all kind of stuff. So that is really good, and you can use Ansible to verify the state. But when you need to have lots of things, and then you can actually need to check lots of things, that doesn't scale. And you can run various commands, but that output's huge, right? So what you really want to know, is it up or down? I didn't want to have output from 50 devices, and that looks like 5 screens each, right? So you don't want to. So for that, unfortunately, I just write my own code to actually do that. So just gets data from Kafka, and it just produces the output saying it's up. So you don't have to do that. And you could potentially write an Ansible module just to, when you finalize in the config, it just feeds it and says it's up, that's done. And it provides with Kafka and the streaming pipeline, it provides the feedback for various systems as well. So because whatever they do to the network, they actually can be verified via the state configured. We're still using Elasticsearch. That is used to store the structured data. So there's a concept of like kind of flat data. So what you store in FluxDB is called flat because that's not really a document, doesn't look like document. It has like value and then several tags of that. So this is not really like typical data structure in that regard. And Kibana, we use Kibana and Grafana for visualization. Elasticsearch is really a thing. It's really fast. We feed IPFix into it. The rate is enormous. I think we do 45,000 documents per second written into that thing. It can do more. And it scales linearly. So you can, the more nodes you add, the bigger the ingestion rate. So it's really fast and really nice. And you can do for 24 hours, which I think will take like millions of documents, it can actually produce the outputs. Like it can show you which, from IPFix feed, which ASs have the more traffic, which IP addresses were the top ones, like goes for enormous amount of data. In Flux, we still use Flux for simple statistics, which is like interface counters and things like that. So that's called like flat data. So it just has the text and some counters as well. Can you do the same with open source tool? Yes, some of it. You could use Logstash to transform your data. You can use the FluentD, which we are mentioned about, to actually collect the data. The only problem, I think, with the things, if you want to react to events and stuff, I'm not sure what would you use. We just write our code, which is just that stuff. The other thing I wanted to mention, there's a new thing called Yandex ClickHouse. Yandex ClickHouse is like it's a column-oriented database, and it's blazingly fast. And they can actually produce, so in FluxDB is limited in terms of the queries you can run. So it doesn't allow you, there's no such a thing as left-right join or anything like that. With Yandex ClickHouse, you can slice it and dice it as well. And it has default built-in connector to Kafka. So you can stream millions of rows into it, and then it's blazing fast. I think today is going to be someone else who is going to be actually talking about that specifically. Cloudflare are using it. It's an interesting thing to look at. And questions? Probably not have time for it. But if you want.
Nothing blazingly pressing. Thank you very much.
Thank you.
Excellent. So we'll just have a break for morning tea, and we'll be back here ready to start at 11. Okay.